Hello, it's Dr. Daystorms, and I wanted to do this lecture on video so that we would have more time to do discussions and or possibly work with problems should you have any questions about these kinds of reactions. And I also didn't want the very first mechanism that we did be on the video, so it's the reason why we did the first mechanism in class. But this next reaction mechanism that we're going to do, and I do expect you to know it, to memorize it, it's very important, and it's going to come, and you're going to be using it throughout the rest of this semester and all of next semester, because many times free radical halogenation is the first step in a large synthesis, because it makes it, you're going to ultimately make an alkyl halide, and alkyl halides are good starting points since the halogen is a great leaving group. So let's go ahead and get started. First, I want to just review something that you should already know from Gen Chem, but it may have been a while, and that's to look at homolytic versus heterolytic cleavage. And with cleavage here, we're talking about the breaking of the bond between two covalently attached atoms. And so lytic, which means lysis, is a way to break something, and then we have homo, which is same, and hetero, which is different. So let's look at how this results. In the example that I'm just going to use right now is hydrobromic acid, but we could have just done any generic A bound to B kind of reaction, or I'm sorry, kind of bond. So in this instance here, I'm actually going to start with heterolytic, which means that the bond is not broken evenly. Okay, so in this instance, and please note the arrow, remember this is a double-sided arrow, so it means that both electrons are going together in the same direction. We always start, so the way that this would read is we have these two electrons going towards the more delta minus bromine, and so we have a heterolytic cleavage. We're left with a proton, the H+, and then we're left with a bromide anion, Br minus, because it has 8 electrons around it. On the other extreme, you could have something called homolytic bond cleavage. That's where the bond breaks evenly, or it's the same between both atoms. And so once again, now if you notice, it's not a double-sided arrow, but it's got a single barb. So one electron goes towards the hydrogen, one electron goes towards the bromine, and we're left with 2 free radicals. Now, free radicals are not going to be happy, so they're going to go on to react with other things. So when we talk about free radical halogenation, it's not an easy thing to do. It requires heat and or pressure in order to get that bond to break unevenly. So now if we think about the reactions of an alkane, and in this instance here, I have a generic carbon-hydrogen bond. Now, there are 3 of these bonds that I haven't specified what they are, and then the 4th bond is between a carbon and a hydrogen. So, what this would state is, in order for it to spawn, let's say that for this to be a homolytic cleavage, we would have 1 electron going to the carbon, 1 electron going to the hydrogen to form a carbon radical and a hydrogen radical. However, this does not spontaneously occur. Okay, why doesn't it spontaneously occur? And the reason being is that it's very, very high energy. So it's energetically unfavorable in order to split apart that carbon from the hydrogen in such a way in order for 1 electron to go to each atom. Okay? So, how can we go ahead and break apart the carbon and the hydrogen in order to do free radical halogenation? This is achieved because the hydrogen atom is simply pulled off by another free radical. So where does that free radical come from? And so the answer to that question is usually, almost always, what we're going to be talking about is it's going to come from a halogen free radical. So if I just have a generic looking halogen. Remember, halogens are naturally diatomically occurring. So we're talking about chlorine, Cl2, bromine, Br2. Those are the two most commonly that are used. So what we do here is you have to add heat, which is symbol for heat. So it's high heat and or light, and this is the symbol H nu. If you think back to Gen Chem 1 or physics, that's the symbol that they use for light. And then what happens is that by doing so, we get one electron, single barb arrow, that goes towards one X. One electron goes in a homolytic cleavage towards the second X, and we get two halide radicals. And it's these halogen radicals that can then go on and to react with the alkane. And it's not picky. It can react with almost any alkane. Okay, and so now let's just talk a little bit about how that would happen. So what we're talking about now is we have this halogen radical, which I'm only going to show the radical electron for clarity's sake right now. And then we have our generic alkane. What happens is it comes in and it pulls off the hydrogen with one electron, and one electron goes to the hydrogen. One electron stays behind with the carbon, and that's going to yield now the alkyl radical, plus it's also going to have the hydrogen halide, so like hydrobromic or hydrochloric acid. Right? So let's look at some of the energy values that would be associated with this. First up, let's look at methane. So if you remember, the methane is CH4. Okay? So the radical that will be produced from methane is called the methyl radical. So in this example, once again, we have the halogen radical coming to react with that bond, and it simply pulls off the hydrogen from the methane group when taking one electron with it, and then one electron stays behind. This is going to result in the methyl radical, and it's going to result in the hydrogen halide. So how much energy does it take to break that bond? So what's the delta H to do that? And it's not important for you to memorize these numbers, but it's 105 kilocalories per mole. So what happens if we come up and let's look at what happens if it's ethane. So instead of methane, let's start with ethane and create what's called a primary radical. So now we're going to create this what will become a primary carbon radical. And in doing so, once again, we have the halogen radical, and I'm just showing one electron, but in reality there's 7 around there. It comes, it pulls off the hydrogen, and please note, this is ethane. I'm just showing, for clarity's sake, the one hydrogen that's being pulled off, and I'm showing it being stuck out away from the rest of them, so I can more easily draw my arrows in. But one electron goes with the hydrogen, one electron stays with the carbon, and we're left with a primary carbon radical. And that's because, and I'm going to really exaggerate the way this looks. The reason being is the carbon that has the radical is touching only one other carbon. And so that's why it's called a primary radical. So would you expect this to have a higher delta H value or a lower delta H value? Remember, the methyl radical formation required 105 kilocalories per mole to break that bond. This one only requires 98 kilocalories per mole. It actually requires less energy to break the bond between a primary carbon and the primary hydrogen. So now let's go ahead and look at a secondary radical. So for this example, in creating a secondary carbon radical, we're going to use our good friend propane. Now I've drawn propane out a little differently than I normally do in class, just to exaggerate the hydrogens on the secondary carbon, but that really is propane. hopefully you kind of get an idea of the way the mechanism is going to occur. We have the one electron from the radical of the halogen coming and pulling the hydrogen off, but it does so in a way where one electron goes with the hydrogen, one electron stays behind with the carbon, and now we're going to be left with and I'm really exaggerating this radical here, but we're going to be left with, once again, two species. One will be the newly formed secondary carbon radical, and the other one will be the hydrogen halide, once again. And so what kind of value would the delta H be for this? Remember, the methyl radical is 105, the primary radical was around 98, while the secondary radical is actually even lower, 94.5 kilocalories per mole. Hopefully you're starting to see a trend here on how easy it can become to abstract the hydrogen off of the carbon. Okay, so finally, let's go ahead and look at this trend even further, and let's go ahead and create a tertiary carbon radical. So now, for this example, we're going to be using 2-methylpropane, and this is 2-methylpropane because, once again, just to review, this was 1, 2, 3 carbons for propane. The methyl group is hanging off of carbon number 2. So this is why it's 2-methylpropane. And then this will be the hydrogen that's going to be abstracted. Okay, so let's review the mechanism once again. We have the one electron from the halogen radical coming and abstracting or removing that proton, or I'm sorry, that hydrogen at this point. One electron of the bond between the carbon and the hydrogen stays with the hydrogen. The other one stays with the initial carbon. And we're going to be left with the radical, which now is a tertiary radical, tertiary carbon radical, I should say, and the hydrogen halide, for example, hydrochloric acid. Okay, and to review, once again, this is called a tertiary carbon radical because we have the carbon radical, the carbon that has the radical is touching one carbon, two carbons, 3 carbons. So what kind of energy is this going to require? It goes from 94.5 kilocalories per mole for a secondary radical down to 93 kilocalories per mole for the tertiary radical. So let's just summarize what we've known so far. What we've been talking about is the ease of abstraction of the hydrogen from carbon. Okay, it's a hydrogen, I'm sorry. So, the order goes, a tertiary carbon is easier to pull off its hydrogen than the secondary, then the primary, and the hardest one is that methyl hydrogen. So I'm going to draw it like that once again. So the question is why? And the Miss America question or answer for all of these when we talk about it in organic chemistry is just think about stability. Just think of the reason why it's easier to pull off the hydrogen from a tertiary carbon is because the carbon radical that's formed is more stable. It's still reactive, but it's more stable than the methyl radical. So what does that mean? Let's just think about the stability of the radicals. What we're saying now is that the tertiary radical is more stable than a secondary radical, more stable than the primary radical, which is more stable than the methyl radical. Okay, so now let's just draw out the reasons why this happens and start to use some logic to explain it. So, there are 2 reasons why the stability trends occur the way that they do. Let's first think about what we know of. I'm going to use methane here as the example. And this is a tetrahedral shape. So the angle between the two hydrogens is 109.5 degrees, and these are all sp3 hybridized orbitals. Okay? Well, what happens is whenever you remove one of the hydrogens, so let's say that we pull off one of these hydrogens and it gets pulled off and it takes one electron with it, we're going to still have our carbon left, but it's going to have 3 things hanging off of it instead of 4 things. And if you remember, when it has 3 things hanging off of it, it's no longer going to be tetrahedral. Now the angle is 120 degrees because it's trigonal planar. But that's not the only thing. It's still, because we didn't draw in the 1 electron that's left behind. That 1 electron left behind is going to be in a partially filled p orbital. Remember, that's the one that looks like a dumbbell. The hydrogens are still there. The 3 hydrogens are the square planar, and they are sp2 hybridized. But that means there's a p orbital left behind, and that is a partially filled p orbital that has 1 single electron in it. And it's not going to be really happy. So that's what methyl radical looks like. Now let's see what it looks like whenever we have the tertiary carbon radical. So let's draw it. I'm just going to draw the radical itself. So we have the carbon, and that carbon now has 3 other carbons hanging off of it. Okay, and it has the 1 electron. Well, what happens is the more carbon substituents that are hanging off of that carbon can help out. They can donate some of their electron density. Because you can think about the fact that they can help donate a little bit of the electron density towards that partially filled p orbital. So remember, we have the partially filled p orbital. Well, those 3 neighboring carbons can help out. And so this helps partially stabilize the unfilled orbital. Okay, because you have 1, 2, 3 carbons that can help lend the electron density. This is called induction. Induction is sort of like having friends help you out. So the more carbons, the better. The more friends that you've got, the easier it is to fill, or partially stabilize that unfilled orbital. Once again, that's called induction. That's reason number 1. There's a second reason as well. The second reason, or reason number 2, is called hyperconjugation. So we've already done induction, which is where the number of carbons that carbon radical is touching affects it, because the more carbons that you touch, the more that they can help loan electron density. Hyperconjugation is a lot like a pi bond. And so if you think back to a normal pi bond, so that was a carbon-carbon double bond. Remember, there was the sp2 hybridization, and then you had the p orbitals that look kind of like the dumbbells, and there's this overlap. Here, let me use a different color. There was this overlap of the electron density of the dumbbells, and that's what caused the stability, the extra stability of a double bond. And each set of dumbbells counts as 1 bond, and so that's why this is a double bond, because we have 1, and then we have 2. Right? So now, how does that relate to the radical? So what happens is you have radical hyperconjugation. So let's draw the carbon. This has the radical on it. So it's got 3 bonds, and it also has that p orbital, that has the 1 electron in it. It's a little dumbbell, but it's only half filled. Because back here we had 2 electrons. So this carbon, though, has its friend next door. I'm going to draw the friend in a different color. And let's say that that friend has, it's still tetrahedral. It's got 4 hydrogens hanging off of it. It's tetrahedral. And because of that, these hydrogens, it's not the carbon itself, but it's the hydrogens on that carbon that can actually help fill up and stabilize that partially filled p orbital. And even though it looks like it's far away, this one is actually just as close to these as the others, because it's in 3 dimensions. Okay, so we have 1, 2, 3 hydrogens hang off of that neighboring carbon that can help partially fill up that p orbital. So let's look at the tertiary carbon radical. So what does that look like? I'm going to draw the carbon radical first. So there's the radical. And if it's a tertiary carbon, let me change my colors. We have 1, 2, 3. 4, 5, 6, 7, 8, 9. We actually now have, instead of just having 3 hydrogens around, we have 9. And since this is in 3-dimensional space, all 9 of these can help lend a hand, so to speak, to this partially filled p orbital. So that's called hyperconjugation. So the more hydrogens hanging off of the carbons, or other atoms hanging off of the neighboring carbons, the better. So we have induction, which is where the carbons next door can lend some of their electron density, and then we have hyperconjugation, which is almost like a pi bond, where the atoms hanging off of the neighboring carbons can help lend electron density. So these are the 2 reasons why the tertiary carbon radicals are more stable than all of the others. And the reason why the methyl radical is the least stable, because it doesn't have any neighboring carbons with it. I hope that this has helped explain a little bit about the way that free radicals form. In the next video, we'll actually then discuss review the mechanism.